Let's get going with Chapter 11, Basic Chemistry, Pearson, Properties of Gases, Pressure, Volume, Boyle's Law. You'll learn all the laws, Charles' Law, Gay-Lussac's Law, and Combined Gas Law. And in fact, Combined Gas Law, it really is Combined Gas Law, deals with all of these gas laws, as you will see. Volumes and moles, Avogadro's Law, and Ideal Gas Law. For the most part, these are really very, very similar gas laws, but they're all based on certain conditions. And gas laws are chemical reactions, partial pressures, Dalton laws. So at this time when the gas laws are being developed, the chemists were really not too shy about naming them after themselves. Okay? So this is kind of how it went. It was a noble thing to do. So let's talk about these gases. And by the way, we will go through the lecture and then we will have a work session where we do work through the problems in more detail. So in the formal lecture part, we won't work as hard on the problem, but we will pause and we'll work through them. Okay? Here we go. We're surrounded by gases. Voila, voila. You know that. Elements exist in gases. These are what? The diatomic gases. And these are the other gases. Carbon monoxide is a silent killer. You guys have worked on that already in your pre-lab work. And this is pretty important to keep an eye on the carbon monoxide poison. Someone in their assignment talked about smoking and the concentration of carbon monoxide in smokers versus non-smokers or something, which I thought was pretty cool to note that. So you basically, even if you're not killing your lungs, it's kind of you reach a certain threshold, not good. So these are gases, low molecular weight, hydrocarbon propanes. These are all gases. And because of that, they exert they exert a lot of pressure upon containers and the environment. Behavior gas is quite different from that of liquids and solids. Gas particles are much further apart. Very important to note that gases have no definite shape. Whatever the container is, that's their shape. Gases are less dense than solids. Very important. The further molecules are apart, the less dense they are. Dense means you're closer together. Okay? It's like going to a Sugarland concert next week or something. It's going to be pretty dense. Right? All right, here we go. Kinetic molecular theory. The kinetic molecular theory of gases states the following. A gas consists of small particles, atoms, and molecules that move randomly with high velocities. They're just going all over the place. Okay, attractive force between particles of gases is usually very small. So these molecules are like marbles, hard marbles. They're just bouncing around off of walls and each other and all around. They don't stick. Gas particles are in constant motion, moving rapidly in straight paths till they hit something, right? The average kinetic energy of a gas molecule is proportional to the Kelvin temperature. It's proportional to this Kelvin temperature, and this is one of the strong areas where the principles of Kelvin makes sense. Pressure. When gas particles strike the walls of the container, they exert pressure. That's what happens. If the gas is heated, the molecules move faster, strike the wall container more often, and increase the force, increasing the pressure. You intuitively know these things. So please do not step away from your intuition on this. But make sure we use the right formulas in calculating the values for it. So here's what happens with pressure. Then atmospheric pressure is the pressure exerted by a column of air from the top of the atmosphere to the surface of the earth. So from the top of the atmosphere, okay, to the surface of the air is 1 atmosphere or a little less at sea level. So that's why it's really called 1 atmosphere. You get it? Because it's the 1 atmosphere. Okay, now you get it. So this 1 atmosphere pressure, whatever that is, that's our common pressure. That's our norm pressure. The volume. The volume of gas equals the size of the container. That's it, in which the gas is placed. If the container is flexed in a container with a flexible volume, adding more particles increases the volume. In a container with flexible volume, adding more particles increases the volume. In other words, the tank starts to, your balloon blows up, right? Okay? You put more helium in the balloon, it goes up. Lowering the temperature of the gas reduces the kinetic energy of the molecule, decreases the volume or space they occupy. You take a helium balloon on a hot day, it looks really beautiful. It says, I love you and everything. You're all excited about it. You go home to your air-conditioned house, you really got it down to about 63, really kind of feeling really good there, and you look at the balloon and it's kind of sagging a little bit. That's what's happening, okay? You decrease the temperature, therefore you decrease the volume. The temperature of the gas is related to the kinetic energy. Kinetic energy of the particles as measured in Kelvin. Kinetic energy, okay? For example, in a rigid container, heating the gas will increase the energy of the molecules and therefore increase the pressure. You're heating it in a non-rigid container, therefore they're bouncing more, okay? Speed up, and voila, we increase the pressure. Adding air to a bicycle tire increases the amount of gas in the tire, resulting in a higher pressure inside the tire. Higher pressure means you're going to be able to ride a little better, right? Usually the mass of a gas is measured in grams. The mass of a gas, and you want to note the units that are used in these equations. Let me make a note of that. So remember that the units are important. Make sure the units match out. Okay, because you might, for example, I might give you the problem in Fahrenheit, but you need centigrade. Follow? Be aware of that. Make sure the units check out. So note the units. So the units for gas, mass is in grams. In gas law calculation, we change grams to moles. Why? Because when we think of gases, we think more of the number of moles and molecules, Avogadro inside the gases. Follow? So if you're given grams, you want to convert to what? Moles. Got it? All right? So when you're doing these gas law equations, they're done in moles. Okay? And so here is a summary of the properties. We won't repeat this, but this is a summary. You want to take a look at this. This is where we'll get our true-false type questions from on exams. This type of a table. Okay? All right? Here, gas pressure. Will billions of gas particles collide with the walls of a container, they exert pressure, which is defined as a force acting on a container. It's a force per area. Keep that in mind. So if the area increases, the pressure decreases. Does everyone see that? Because they're inversely proportional. If the force increases, the pressure increases. Okay? 1 atmosphere is defined as exactly 760 millimeters of mercury. That is by definition. That is the standard. And that's also called 760 torr. Exact. This is an exact number. That is what that number is. If this is an exact number, will you use this number in determining sig figs? No. Okay? It's an exact number. We don't use it. And 1 millimeter of mercury is 1 torr. These are conversions. Yes, I will put these on the exam. Okay? You will see them. Okay? SI pressure is measured in pascals. 1 atmosphere is shown here in pascals, okay, or kilopascals. So keep this in mind, and you'll know when to use what. The key is to match. I'll emphasize again, is to match the units. If the problem's working in atmospheres, then you want to use your pressure in the atmosphere. You follow? If it's working in pascals, you want to convert your pressure to pascals. So you have to do conversions. How would you do the conversions? Using what? Dimensional analysis. Even though you know it's very simple to convert, right? You just divide the number out, right? I will look for the process. Here we are. These are units. I don't require you to memorize these, but I think, it's just kind of good to be aware that 1 atmosphere is 760 millimeters of mercury and torr. It's just good conversation when you're walking down the hall with the department chair of chemistry, right? And it shows that you've been in my class. You say, by the way, I've been in Dr. Revis' class, and I know that 1 atmosphere is 760 millimeters of mercury. Got it? That's how important that information is. All right, atmospheric pressure changes with the altitude and the weather. And so we just kind of show you how it goes from here, right, to here. Okay? Okay. So you have 1 atmosphere here and less than 1 atmosphere on top of the mountain. And here it shows you it's 760, Las Vegas is 752, and Mount Whitney is 440. And people who visited these places say they can tell the difference. And senior citizens say they can tell the ache in their bones are talking to them, things like that. Okay? All right? So here, let's start talking about these laws. These laws are, for all intents and purposes, here comes a really ugly word that I said never mentioned in my class. Ratios and proportions. How dare we? These, for the gas laws, working through the dimensional analysis, have been summarized into laws. Recall we said we work by what's called the scientific, we use these scientific hypothesis principles, right? Okay? And we go through hypotheses, observations, experiments. We go through all of these things, right? And occasionally we do it so much we decide that it's a law. That's what happened with the gas laws. It became very clear that these are standard laws. And more times than not, when there are standard laws, the equations are written to establish them as the law. Okay? And so Boyle said that Boyle's law does not consider temperature because it's constant. Here's how you know. When it says, and you want to note this, when it says that it's constant temperature, that won't show up in your equation. If it says it's constant pressure, that won't show up in your equation. If it says it's constant volume, that won't show up in your equation. So whatever is constant, do not write that in your equation. Whatever you do, don't write that in your equation. You got it? Okay? So when we do go through work session, I'm going to show you one way to look at one equation and have them all in your head. Okay? So Boyle said that the pressure of the first time the pressure of the volume has to be proportional to the pressure of the second time the volume of the second. That's it. For those of you who are having difficulty rearranging these equations, talk to me. I'll tell you a fast way to rearrange them as we're sitting around, okay? I won't do it in the formal lecture. I'll show you how to quickly rearrange these, all right? I'll show you quick math. Otherwise, Google it, watch a video to rearrange them. So Boyle's law is an indirect relationship between pressure and volume. An indirect relationship between variables means that the one variable increases, the second variable decreases. You get it? So in other words, if pressure, since they're on the same side of the equation, since pressure goes up, volume goes down, pressure goes up. You get it? That's what that says in math. So this is basic math. If you're having trouble with that, let's talk about it at the break, and we'll address that individually. Okay? So, but this is the equation, and you get to hang on to it and use it. So, let's see. So here's a problem, and I'm going to show you something here. Let's see. We're going to walk through this, talk through it, then I'm going to tell you how to look for it, and some tricks to do. And some of you are going to listen to this, and some of you are going to say, I don't need to do that. But it'll save you. It'll save your hide. Okay? When Whitney had asthma attack, she was given oxygen through a face mask. The gauge on the tank was 12 liter, and the pressed oxygen read 380 millimeters of mercury. How many liters would this same gas occupy at a second pressure shown here if the temperature and the amount of gas do not change? Temperature and amount of gas did not change. We know if the temperature and amount of gas do not change. So we know the temperature here is what? Constant. Does everyone follow that? We go back and we look at P1, V1, P2, V2. You will always know what equation to use if you follow the next thing I'm going to show you through all these gas laws. I'm going to show you how to know which equation to use, because you're going to use Boyle's, Gay-Lussac's, Frederick Douglass. I don't know. Okay? I'm going to show you how to do it. Follow? If you follow this process, more times than not, you won't miss it. On your paper, as soon as you see the problem, write the V's, T's, or whatever above them. Whatever you see, that's what you're going to use. That's the equation. So watch this. You ready? She's given V1. So I put a V1 right above this, right away. You get it? And this is P1. So I have V1, P1 on my paper already. With me so far? How many liters would occupy at P2? I put P2. So everyone see what I just did? I could write that on here. Sorry. Okay, so this is V1. This is P1. This is P2. I'm done. I have V1, P1. What's P1? And I have P2. What's missing? That's what I'm looking for then. You get it? So it's just, I'm looking at the equation. P1, V1 equals P2, V2. That's the equation I'm using. But I'm looking for V2, so V2 equals P1, V1 over P2. I'm done. If you write that on your paper, you'll be looking at your equations to use in all of these problems. If you see gram, we don't use grams, right? What do we use? Moles. Put it in there. You got it? Mole, N is a symbol for moles. So put it in there, and you'll be looking at your equations. Okay? The gas laws is a law. It does not change. It's very rigid. Okay? It's fixed. All right? So keep that in mind. Everybody follow that? So we have that. So if you do that, you'll be able to solve this problem simply by setting this up. Now the author's going to go through and show you how he did it. So here it is. You see how he did it? He knows he's looking for V2. So you hold that constant, move everything around, showing you how to cross out all the math. Some of you just know how to do this in your head. You get here, you run the numbers. That's it, folks. So the only thing you have to really watch for here is what? Sig figs. Okay? And we know it's 12 is two sig figs. It's, yep, 2 and 2, so that worked out, right? So everyone follow that? Watch for the sig figs. So if you do that on your paper over and over again, now that's going to drive some of you are not going to do it, but you'll see equations. They always work themselves out that way. There are no tricks to this. During inhalation of lungs expand, the pressure in the lungs decreases. During inhalation of the lungs expand, pressure in the lungs decrease. Yep, you get it. You guys who worked in the medical profession, you kind of know this already. Air flows toward the lower pressure in the lungs, and it pushes your diaphragm. And it's diaphragmatic breathing. Anybody play woodwind instruments? This is why they talk about diaphragmatic breathing. You get more pressure that way than breathing from your chest, not from your chest. All the band directors keep screaming at you. You're breathing from your chest. Get better pressure that way. Charles' law, piece of cake. You can do it, right? Charles' law states that the temperature K of a gas is directly related. Temperature K. Temperature what? K. So when we do this, we have to have temperature in what? In Kelvin. And we'll take a look here. Occasionally you'll see, well, I won't get into that. Because of proportion, well, we'll just see where we go. And we'll tell you some other things later, okay? The temperature K of the gas is directly related to its volume. V, when P and N, the number of moles, are constant. Okay. If the temperature K increases, then the volume also increases. So if C increases, K increases also. You get it? So just it's the temperature, right? The principles are based upon the Kelvin scale. Okay? But the relationships, because it's this law, are the same. Okay? Charles' law is a direct relationship between the volume and temperature. A direct relationship between the variables means the variable increases, the other decreases. You know this now. No change in the number of moles and pressures, so we write it out, and what we have it really is V1 over T1 equals T2 over T2 for Charles' law. Okay? With me? This is it. This is the law. For those of you who like to memorize, yeah, we found your zone now, right? All temperatures used in gas law calculations must be converted to Kelvin. So you can guess that someone like me might give it to you in Fahrenheit, right? You know why, right? Because that's going to make it take Fahrenheit to what? Centigrade, then centigrade to Kelvin. You get it? So watch for me doing that to you. Okay? All right? That's where that formula for Fahrenheit did not go away. So, calculating volume, temperature. Helium gas is used to inflate. Okay, let's see if we can work this out too. You're going to work this the same way we did the other one, right? Helium gas is used to inflate the abdomen using, blah, 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 laparoscopic surgery. Does everyone see what I just did to that? Don't get stuck on the verbiage, right? These laws simply work with the values. The sample of helium has 5.4, 15 degrees C. As soon as I see C, what am I thinking in my head? There you go. Very good. What is the final volume in liters of the gas when the temperature has increased to this? So right away, I know what equation to use simply by writing this up, right? This is what? V1, and this is T1. So I'm using that equation right away. Does everyone see? And they told me I'm looking for V2. And they gave me T2. Does everyone see that? So that tells me which one of the equations I'm using. I'm using the V1 over T1 equals V2 over T2. Follow? It's telling me, if you write them in there, you'll see it, which equation to use. So, it gets back to that question, what are you looking for? It's the one that's absent. Okay? It's the one you don't have in these gas laws equation. And we do this over and over again. Yeah. Lots of fun for chemists. Okay? So we rearrange the equation. I'm not going to go through this. We'll do this at the break when we go work through the problems. For those of you who may be struggling with rearranging it. Rearrange it. We punch the numbers. Notice the units here. Where do we get this from? What do we know happened to this? This is what? Centigrade plus what? You got it. Does everyone follow? And this is centigrade plus 273. You want to keep that in mind. And you punch the numbers through, you check your sig figs. This is how we do the gas laws. Okay? And we repeat it. So now we come to Gay-Lussac's law. What do you guess is going to happen now? Similar principles, right? The pressure, Gay-Lussac's law states that the pressure of a gas is directly related to its temperature when V and N are constant. So when it says these are constant, you don't consider them in the equation, essentially. Okay? If the pressure P increases, then the temperature K also increases because we do this in K. And someone like me would give it to you in F just to make you do that calculation. So Gay-Lussac's law says then P1 over T1 equals P2 over T2. No change in volume and the number of moles. There is no change in number of moles or volume. All temperatures using gas law use Kelvin. Not Kevin. Kelvin. Okay? So we do the same thing here, right? Home oxygen tank can be dangerous if they're heated because that's right. They could explode and you know why. An oxygen tank has pressure of 100, so that's P1, right? So I put P1 and this is T1, and the temperature, if the temperature of the gas inside the oxygen reaches this, that's T2. So I know what I'm looking for. Next is what? What's missing here? P2. That's the equation I'm going to use. Okay? If you mark them on your paper right away, you'll see which equation to use. You'll know what's missing. And so we do this. The oxygen tank may rupture if the pressure inside exceeds 180 atmospheres. Would you expect it to rupture? So you go through, you put the numbers in, and let's see what it ruptured. How many did it say? What was the rupture temp? I mean pressure 180. What did we hit? What do you think?
Yep.
Yeah. Not good. This is why we do these kinds of things. This is why we learn these principles. Okay? So it's not that we're learning them just to have fun as chemists, but it actually is part of safety and handling materials. So we're going to get these equations and get how we do them. We'll work through them. Vapor pressure is the pressure above the liquid at equilibrium in a closed container. At the boiling point becomes equal to the external pressure. At the boiling point becomes what? Equal. You get it? The external pressure. So it then becomes equal, it just escapes, and it can now equilibrate. So that's what happens when things start to boil. It's trying to say, oh, I'm there now, I've reached that vapor pressure. Voila, I can come out of my shell. Okay? Boiling point of water depends on vapor pressure. So here, this table, I'm not going to ask you to memorize this table, and you know how to, this comes from what? Using these gas law equations, right? And we know it's in degrees C, but when we run the calculation, we use Kelvin. And so at 0, vapor pressure is 5. At 100, the vapor pressure reaches 760, which is what? 1 atmosphere. That's where water boils. Okay? But we know in Denver, this is less than that, right? Okay, which means that it boils faster at Denver because it's about 740 or 50. It's about mile high, right? It's less than 760. Okay, in Denver, and therefore it boils faster. An autoclave used to sterilize equipment attains a temperature of 100 degrees C. Increasing the pressure increases the temperature. So in other words, you want to superheat this. And you put it in the autoclave. And you guys are more familiar with this than I am. Okay? And this is what dentists do all the time. Dentists. And this is what should be done at the nail shop and at the spar. That's what they should be doing. Right. Okay? It should be autoclave. Okay? And they say that it is. I trust them. I really do. Okay. All right. That brings us what's called a combined gas law. The combined gas law just simply looks at all these gas laws. They're all put together. Someone said, wait a minute, why don't we just look at this as one big gas law? And that's essentially it. It's telling that the ratio of the pressure to volume of 1 over T, of the pressure volume in the second set to temperature has to be equal. Incorporates all the pressure volume temperature relationships for gases previously studied. All of it, puts them all together. It just was studying the effects of changes in 2 of these variables on the 3rd variable. You get it? So occasionally you'll be changing these. So how will you know when to use this? You mark everything down through a problem. If you see pressure, volume, and T, you say, oh, must be the combined gas law. You get it? But when watch this, and I'm going to show you, these are the same equation. If temperature is constant, you just erase it out of the equation. And you're using P1, V1 equals P2, V2. If volume is constant, and it doesn't have an effect, you erase it out of the equation. Get it? If pressure is constant, you erase it out of the equation. So this combines all of them. But you'll know which one to use simply by marking what's in the problem. Because these are laws, they're set, they're standard, they're done the same way. There are no tricks. The only thing that might feel like a trick, is when someone like me, puts Fahrenheit on there just to make sure you awake in my class. Okay? So I'll put it on just to make sure you heard me. Okay? And this is what it looks like when you summarize the summary of the gas laws shown here. You get it? You're really starting with the combined gas law, and it breaks out into Boyle, Charles, and Gay-Lussac. They say, why write all of this when we know temperature is constant? You get it? Why write all this when pressure is constant? Why write all this? So really good mathematical idea. So here we have a problem. So let's see if we can use a combined gas law to see if this problem fits, right? We have a 25 mil, so that's going to be V1. So I'm just going to write and see which gas law I use. That is really not working well. V1. And I have what? P1 with me so far. And I have T1. And which unit should this be in? Kelvin, right. And for these problems, I'm absolutely happy if on your paper you do this. If I see that, I know you know what you're doing. So everyone follow when we do these problems. Okay? I know what you're doing. I see that on your paper, we're good. Okay? You won't have to explain that to me. That tells me you know, because you put it right there with degree C, telling me you know what you're doing. If I see it somewhere else on paper, I might not know what it is. But I'm okay if you put it right there. Does everyone follow? V1, P1, T1, and what do we have here? We have P2 and T2. And so I'm missing what? V2? So that's what I'm looking for. So I know which equation to use. Okay? Whatever's missing is what I'm solving for. And I rearrange the equation. There we have it. We convert. We check the number of sig figs. We're good there. Okay? Keep in mind, I round things off when I'm teaching many times, okay? But you're required to do sig figs into a problem. Okay, continuing with this chapter. We're now on gas laws. We're at Avogadro's law, where the volume of gas is directly related to the number of moles of the gas. So it's directly related to it. If the number of moles doubles, the volume must double at constant temperature and pressure. There you have it. That is the relationship. Okay? So more moles, what happens? Pressure. Okay? And that's what Avogadro says. And we know Avogadro's number then would perhaps have to be used at some point, but that's his law. In this particular case, we always use moles. So here's a problem, and we just work through them. A balloon with a volume of 44 liters is filled with 2 moles of helium. What's the final volume in liters if 3 moles of helium are added to give a total 5 moles of helium if the pressure and temperature do not change? Okay? So here we have it. You can go through, mark up all your things, but again, on the exams, I don't use anything you mark up here. That's only a trick to you. You don't have to mark it at all. You get it? I don't care if you mark it. I was telling you a way of tracking yourself to tell you which law to ID when you get stuck. So that's if you get stuck. So what happens is we rearrange it, and we see that it's this formula, and so therefore this is the final formula I'm using, and then I can go through and say V2 equals this, carry it through, because I clearly see that it denotes V2 equals this. I see the equation that I'm using, and if you choose not to use the equation, here what you would do, for those of you who don't want to do the rearrangement, can do it mathematically, that's fine, except up here, I have to see this with the rearranged, or simply put your values in here, and I will know that you rearranged to get here. Does everyone follow? The values have to be here. But if I see without these indicators and just this somewhere, because what you would have had here, you'd have had some other values under there where you cross out your math. That's a cross out math. That's fine. That's great. Happy. No problem. Okay? I don't grade the cross out math. I grade the formula with the units properly aligned. Because everybody's going to do their cross out math differently. I am not going to go through that part. Does everyone follow? Okay? I see here. I see values in here. I assume your cross out math must be in the right direction. Or I see this formula equals carried through. Those are the only 2 things that I care about. So here, standard temperature and pressure, molar volume. There's this thing called STP, and you will want to memorize this. If you don't, I'll give it to you. 22.4 liters is approximately equal to the volume of 3 basketballs. But essentially, this is 1 mole of any gas is 22.4 liters. So on your problems and in working these, you'll hear it say STP. That means it has a standard temperature and a standard pressure, volume, etc. So if you see that, I've given you those values. And the volume is what? 22.4 liters. If I say it's an STP. Does everyone follow? And it's what? Okay, and it's 1 mole, so you know it's at STP. All right, it's 22.4. You get it? So here, the volume of gases can be compared to STP when they're the same number of moles of gas. Standard temperature, what's standard temperature? 273 K. So this is what it is. So if I ask you on the exam, what's STP, you would tell me the volume, the temperature, etc. What's standard? Okay? So you have 1 mole of helium, okay, that number of grams, and it kind of goes through it, and it shows you that it's still, that the volume is what you have here. So everyone follow that. This is called STP. It's the same calculation you've been doing, but it's defining STP as some set standard volumes. If it's STP, do you use those numbers in your sig figs?
No.
Got it? So here you have it. When a gas is STP conditions, its molar volume can be written as a conversion factor and used to convert between moles of gas and volumes of the liquid. So if you know 1 mole of gas, is this. And so therefore, if you need to go from liters to moles, if you see a problem, you say, I'm stuck, I need to go from liters to moles, you're using STP. Liters can be related to moles, and you will have a problem like that to work. Okay? With us? So here, he used dimensional analysis to carry it out. Therefore, if you use dimensional analysis, you don't have to show any formulas. Does everyone understand that? But if you use formulas, you have to show where they plugged in, and that's critical. Okay? Dimensional analysis, no formulas. Formulas, you show what's plugged in. And to be clear, yes, I'm going to be very anal on that. So here, that brings us to the ideal gas law. The ideal gas law says that the pressure times the volume is related to the moles and a fudge factor, a constant times the temperature. This was found to be a universal standard that allowed you to relate the moles and temperature to the pressure and volume. This is a standard constant. We look it up on a table. Okay? In this class, some homework may ask you to calculate R, I don't recall. But on the exams, I never ask you to calculate R. Okay? I might ask you to calculate P, V, N, and T, but I don't ask you to calculate R in this class. So don't worry about rearranging equations for R. I do not ask for that. You may have to do it on the homework problems. I don't recall what I eliminated there. Okay? The ideal gas law is a combination of 4 properties, P, V, N, and T, written as a single expression. Okay? And R is a constant shown here that helps convert it. I will give you R on any problem we have to work for this level of chemistry. You were doing the upper level of chemistry, I don't give you R. Okay? For this level of chemistry, I give you R. Let me get through. Okay. Here the ideal gas laws combine 4 properties. We show you what they are, and you know 760 millimeters of mercury is what the same as torr. And so here just showing you different units for using the same R. So R can be here, or R can be here. On your exams, you would have both R's. So what am I looking for? I'm looking for you to observe the units. In all of these, you must, let's be clear on that too, you must show me units in all of your calculations for these. I must see the word liter behind it. I must see ATM, millimeter mercury, degrees, whatever you use. Okay? You will lose points if you don't show those. Okay? And yes, I would probably know what they are. The ideal gas law, when working problems, uses the ideal gas law. The units, okay, of each variable must match the units of R. That is what we're talking about here. So, you'll take a look at the R that I give you, and you'll convert the units if you have to. Okay? Okay? On the quiz, I will be giving you one on the quiz where you will have to do the conversion. Not of R, but you would probably have, like, for example, R would probably be in atmospheres, and you'd have it in millimeters of mercury. You have to do the conversion. You get it? You will have one like that. Using the ideal gas law, okay, dinitrogen oxide, you know this dinitrogen oxide because these are all non-metals. They're on the far side of the right side of the periodic table. Laughing gas, what is the pressure in atmospheres of this number of moles of this? This can be done by unit analysis, but because the gas laws are laws, we permit formulas, okay? So we use the formula, PV equals nRT. We can go through and we can, if we marked up this paragraph, which is not required, but it's helpful, we would note we have the moles, we have the temperature, and we have the volume. Moles, temperature, volume. Aha, we must be looking for pressure because R is a what? Standard. So we rearrange the equation, and we punch the equation through, and we get this number. I see this equation, I see this equation, I know they match. If you choose not to rewrite it, then here I must see the moles plugged in, R plugged in, T plugged in, V plugged in. Oops, it turns out to be the same thing as this. Get it? In this case, if you had to do volume, you would put all the other values in here and leave volume sitting there at your X for those of you who like to use that approach. Molar mass of gases. Another use of the ideal gas law is to determine the molar mass of a gas. The molar mass is in units of what?
Grams per mole.
Grams per mole. Very important is gram per mole. This is why we emphasized earlier that you use gram per mole. It often likes to just use gram, but he is stating in front of that it's molar mass. When you get here, if you don't recall the gram per mole, you screw your problem badly. Okay? So dividing the mass of the gas by the number of moles gives you the molar mass of the gas. So there you have it. Given the mass in grams of the gas, we can calculate the number of moles of the gas using the ideal gas law equation. So essentially you can relate molar mass to gases through the ideal gas law. And here we show you an example. What is the molar mass in grams per mole? You know here he's stating it. Gram per mole of a gas if 3.16 gram sample of gas, that number of atmospheres, degrees C, occupies that volume. For those of you who like to mark all over your paper, you will mark it in, and it will tell you that you're using the ideal gas law. You have N, so you would write the N equation. You don't have to do the rearrangement, but you would have to put the pressure in here, the volume in here, R in here, and T in here as your second step in this, in doing this. Does everyone follow? For those of you who like to rearrange the equation, you rearrange it, and then you put them in. Okay? Does everyone follow? But I will have to see them associated with the variables within there. I will not be using this to judge whether or not you had the right associations. Okay? So we have those, and we plug them in. You run the numbers, you got the moles. Mass per moles is permitted. It is a legal ratio. So we take the grams divided by moles equals this. On the other hand, you could do this whole thing in one long dimensional analysis. Okay? If you choose not to memorize these formulas and use dimensional analysis, then go for it. Okay? But I do require you to know the formulas for each of these laws. That's why we're pushing it this way. This is knowing the law. Okay? And I'm like a state trooper. There's no negotiations on this. Okay? I'm hardcore. Sorry, but I am. Gas is a chemical reaction. How many liters of CO2 are produced from 752 millimeters of mercury and 24 degrees C? You're already thinking Kelvin, right? You know to make that conversion. For that number of grams of limestone, what's the very first thing I have to do when I see an equation?
Balance it.
Yeah, don't forget that. That's going to kill some of you because you're going to forget that. You have to balance the equation. In this case, I think we already balanced it out. I see a 2 in front, so it must have. Looks right? You have 2 chlorines, so that's probably going to be right, too. Okay, thanks. All right, so now, here, you needed to get the moles to use in the equation, right? So what's the only way we can get the moles is to use periodic table using what, though? Dimensional analysis. You get it? You got to use dimensional analysis again. Does everyone follow? Okay? And I'm going to try to remember to do the same thing I did on this quiz, is put hint. If you see hint on there, I'm trying to tell you to watch for doing a dimensional analysis in it, okay? And so we have this carried through, dimensional analysis, and we use the problem. On the other hand, you could carry it right on through. So here we have the volume. This case, the equation was rearranged. If you choose not to rearrange the equation, you will write this and plug the values in and then run your math on your fingers and toes or your calculator. Here the equation is rearranged here to go here. Okay, so everyone follow. Okay, I'm emphasizing that no, I don't require you to rearrange the equation if you know how to do the math. I'm okay with that, but I do require me seeing it in the equation. Okay, that tells me you know where the right associations are with the right units, because it's the unit analysis that gives us the answer. So everyone follow. So I would look at this, and if the units are off, I know right away, regardless of what you did in your rearrangement, your answer is going to be wrong. So everyone follow? Okay. Then there's Dalton law. And this Dalton law is a pretty straightforward law. It just says pressure, you guys, it kind of makes sense, right? Intuitive, right? The pressure inside the balloon equal to the pressure of all the gases in the balloon. The pressure in the room is related to all the pressure of the gases in the room. That's the law. That's the way nature has it. So here, total pressure is the sum of the partial pressures. So if you know, if you have three gases mixed, then you have to add up the gases, the pressure of each of the gases. The total pressure of two gases is the sum of the partial pressures. This is 2 atm, this is 4 atm, therefore this is going to be 6 atm. It is that straightforward. Do not complicate this one. But what would happen on an exam would be something like, I would give you two problems, right? And you would have to find the pressure of one and the pressure of the second by using what? PV equals nRT, or P1V1 equals et cetera, the laws. And then you would add them together to get that. Here, the air we breathe is a partial pressure of nitrogen, oxygen, and it doesn't show you the percentages on here. But these are the pressures. You don't have to memorize this, by the way.
We do?
Do not.
Oh, okay.
This is illustrating the principle. This is the real life part of the principle. And this is how we know it works. Well, guess what, folks? I think you survived chapter 11. Thanks. All right, that's it.